Record too. Oh, 3 times recording. Oh, that's interesting. Let's bring it back here. There we go. All right, so based on the last lesson, I hope you had the time to try out these examples. Okay, um, let's review lah. Example 17. So if it gives out heat, it should be a minus here. You start with here first. Q supplied should be a minus because supply means going in. If you are giving out, then it's a minus. There's no change in volume, so your delta V here is 0. And because of first law, so remember we talked about this. Because of first law, this is 0, this is minus 200, so your delta U is then minus 200. All right, so if we do the second one, again, supplied with 70 joules of heat. Start with the first one, put it here, plus if you want to put in the sign, internal energy increases by 100 joules. So plus again, and that will give you 30 over here. Right? So it's based on this. 50 joules of work is done on an ideal gas. So work done here, 50 joules. 50 joules of heat is removed. So minus 50. So this is 0. So you should go through all of this lah, to make sure that you understand whether it's a plus or minus and where you're putting it correctly. And you have to use the equation to figure out the third variable. So usually the first two, for example, like this is given, then the third variable will be a question mark. You need two known variables to figure out the third one. There must only be one unknown in the equation, right? So let's move on. Ideal gas does 100 joules of work. Now, this is a bit tricky. So if it does work on the surroundings, it will be losing. It'll be losing work. So this will be a minus 100. At a constant temperature now, you might want to put this as 0, but actually it's not correct. Constant temperature is related to this because it's 3 over 2 nk delta T. So there's a change in temperature here. Therefore, this should be 0. And then this must be 100 because 100 minus 100 equals 0. So again, use the formula, the first law of thermodynamics, to figure out the third unknown. Try it. Example will be this. This current one, 100 joules minus 100 joules. That give you 0. Okay, the next one, an ideal gas absorbs. So it'll be heat supplied, so it's plus 1,000 joules here. But it does 500 joules of work. So this will be minus 500 joules. And then this becomes 500 joules. Ideal gas supply is 70 joules of heat, so plus 70, 500. Then you figure out the last one. Okay? Um, for questions like this, I think we might have done this before. Yeah, we did this before, so I'm gonna skip this. Okay, there we go. Um, in process AB, so this is your Q in, and then this is your Q in. So A delta U increase equals to Q in plus W on. Your Q in is 150 joules. And there's no change in volume, so it's plus zero. And that'll be the answer. Okay. In B, A, B, C. Now, it's about internal energy change. So what you can see is uh, you can approach using this, which can be expressed to this. The reason why I encourage you to use this because A, B, C is the same as going A to C lah. Then you can get a P1, V1 value here, which is 3 times 10 to the power 4 times 2 times 10 to the power minus 3. And this is 8 times 10 to the power 4 times 5 times 10 to the power minus 3. So I'm taking this and this and this and this. How do I get from here to here? Ideal gas equation. PV equals to NKT. So you can change with a delta V. You can put a delta there. That give you the change. Because we start from here, man. NK delta T. The T is the one that changes. The N and K remains the same because in the ideal gas, the number of, in this situation, the number of gas molecules remains constant. K is a constant, T is the one that changes. And then if you convert, then P and the V may change that accordingly over here. So for this answer will be final minus initial. Okay. Yeah. Now, I guess you're wondering why we never consider B. That's because we are finding the change, and change is before and after. Internal energy is based on a state. State, as I mentioned before, is about your final and the is about the product of your PV. So your final and your initial matters. In between what happens, it does not matter because it's total, it's about internal energy change. All right, so we didn't consider B. So what I'm trying to say is internal energy is about PV. If you know your final PV and initial PV, then that's all you need to know. The total heat added in process AC is over here. Now you should get your answer in B. So if you use this, then you should know the answer in B. Q in is what you need. And the next part is the W on. The W on is then this. It's the area of trap. Now, why is that so? Is because W on is equals to minus integration of P respect to B. That's the general formula. So make sure this is negative. You must have a negative here. Besides, it's expansion. If it's expansion, then it must be negative. Okay? And that concludes the solutions for the examples. So, moving on. Um, the next part of the topic is O-level stuff. So you will find this familiar to you, lah, which is why I'm reserving this for Zoom session, because it's quite easy to understand. First thing you want to take note is heat capacity. So basically, this topic is about how much the object can take in heat, how to calculate the heat based on the temperature, how to calculate the heat taken in or given out during a state change. Okay, it's all related to thermophysics because there is always the Q in area. So this part, right, it could be this, or it could be this. Seldom lah, this one. Maybe some questions will have. So that's why it's important and there's the relationship there, which is why you have a section like that. This is a good 1 mark definition. So make sure you memorize that. And then the formula is similar to your O-level definition. Then this one as well. The difference is per unit mass for specific. So if you see specific is per unit mass. If you see heat capacity only, it's not per unit mass. It's based on the whole body. Okay. This one you can read. And then this one, you will need to use PT equals to MC delta theta plus big C delta theta. So this is a big C. And then this is a small c. And the time is here. Kilowatt, make sure convert to watts. Temperature difference, 45 minus 25, so try it. Okay, and there's always an assumption to be made. Like this one, assume there's no heat transfer in the surroundings. Sometimes they may also ask you in a question. Okay, this one is slightly more difficult. So it's about heat gain equal to heat loss. So the heat gain is the paraffin. So MC delta theta paraffin. equals to mc delta theta copper. And the copper itself, so the delta theta plays an important role. So when expanding out, because this is a heat gain, so is x or t lah, t minus 20, and this one would be 500 minus t. So the order makes a difference. T minus 20 and 500 minus t. Uh, if you put t 20 minus t, and if you put it like this, you'll never get an answer. The answer will be wrong. Okay, so the order makes a difference. Heat gain means temperature increase, so this one will be larger. Heat loss means temperature decrease, so this one will be larger. The larger must come first lah. If not, you get negative. Then your answer will be very weird. The math will not make sense. For the next one, it's about latent heat. Latent heat is due to state change. Okay, so again, 1 mark definitions to memorize. Be sure to memorize them. And then this is the formula. So this is also the heat loss and the heat gain. Heat loss here goes to heat gain. Come out with the equation first. So when you see two objects, two substances, this is substance 1A, that's substance 2. There will always, and their temperatures are different. So that's when you know it's a heat gain or heat loss. That's when you know that you need this equation. So determine the final temperature after the ice has melted. So after it has melted means that you are looking at the MLF, F for fusion. Okay, then this one will be MC delta theta. So again, the bigger number comes first for delta theta, and then you can solve for t. Let this be t. Um, so how do we relate the first law to heat capacity and latent heat? As mentioned earlier on, the first law always have a Q in, and the Q in can be calculated by MC delta theta or ML. Um, so when you have heat capacity, when you increase the temperature without state change, you will also increase the delta U uh, because the kinetic energy will increase. The for during this point in time, the intermolecular forces of attraction will change a little bit, but not significant because it's not a state change. Okay? So all of this will affect your delta U. Now, if you are not changing to gas, so your volume will not change. That's important as well because there's very little work done against the atmosphere. If you're changing to gas, then this will be different. That's why I talk about it here. There's a work done here. So you really need to look into the questions lah. I think this table is good to have, but more sense can be made of it when you do a question. So read this, keep in mind, and when the time comes, I believe it's a TYS 10 series questions that come across with this. So anyway, just take note. Yeah. The rest you can read. Not necessary to know, but yeah, just read. Okay. So what is next? First, congratulations, you have finished everything for thermophysics. Yay. Now I believe I gave you paper 3 as well. But there's more first law to be done. In fact, you should be doing this kind of first law. Um, so I'm going to give you this as homework within the next 2 weeks. Finish them. Yay! All right. But I'm not going to just throw it to you and then you try. I'll give you a few pointers to take note of. Starting with the first question. So first law of thermodynamics 2017 prelims paper 3. All right. Let's take a look at this. First thing you want to take note of is there are values of P and V. So remember I said each point here you can find the PV and that'll be the U. So example, the thermodynamic temperature of the gas at B. You can use PV equals to nRT, 3 moles. All right, use that to find the T. Change in internal energy, BC. What do you think? 3/2 delta PV. So go and try it. Work done in process BC, area under graph. Heat absorbed in BC, everything all in BC. First law. U increase equals to Q in plus P W on. There you go. Question 1 done. Easy. Next. Uh, remember this? So try it. Use the ideal gas equation to solve. So one key thing to take note, a very um, a good hack, a good habit is to write down all the equations that you know of. You can even put first law as well. And then see what you can put inside and solve the question. Okay, use first law to explain. So, uh, why the temperature air changes? You have work done, okay? Change in volume. So you can find there's work done here because of change in pressure and the volume. Um, it's suddenly compressed. Suddenly it's fast. So your Q in is then zero. Your W on is not zero. So your internal energy is not zero. And we know that this is 3 over 2 nk delta T, which means that this is not zero. Okay? Okay, this question may look intimidating, but it may not be lah. Right? This is a simple heat engine. You can use this to heat up a place. Or you can use this to um well the most modern application would be a car combustion engine lah. But to explain that is a bit difficult at this point in time. It's complicated. Anyway, a heat engine is simply an engine that provides heat from mechanical energy. Mechanical energy means like kinetic lah, movement. Oh wait, it's the other way around. Huh, interesting. Okay, it's the other way around. Well, you can go both ways lah. You can either, in this case, you're heating up, then this thing will move. But you can reverse it. You can keep oscillating this platform and then you produce heat. So for this question, is another way lah. So if it's the way that I mentioned is a car. For this one, oh yeah, okay. This is how a car works basically. Because the car will produce heat, then the platform will move. So let's explore this. Initially no load, then you load, then you leave, then no load, then you go back. So during this loading, there's heat involved lah. So the first thing you want to do is to fill in this blank here. All right. So what can you do to fill in this blank? If you're given pressure, volume, and temperature, And taking note is an ideal guess. So you know this answer. Why the pressures will be the same? A and B. No load, mah. Then you only left with atmospheric. Okay? Oh, done for this. So how to get D out? P and V. So find your marking, your P and D, P and V, or D. Estimate the work done. Now you see estimate, maybe you need to count squares or trapezium. Work done is always area under graph. Q is um you might need to use first law for this. Okay. So think about it. So this will fall under the recent topic that we did just now. We have this. Hmm. Rate of temperature rise become very small. It is not boiling. If the first answer that comes to your head, oh, it must be boiling, it's not boiling. Think of something else. Is water is at 60, is at 57.5 degrees Celsius. What could be happening? All right. This one you should be able to do it. So I'll leave it up to you. Internal energy is 3/2 kT. NKT. And then it's 3/2 PV. Okay, I've done this for you before. Again, you have PVs, use them. Right? Now you can see that the pattern repeats itself. Lah. So I encourage you to try taking note of what I have before, the relevant formula. Okay? Yeah, a lot of the questions you need to try. Lah. This is 3/2 NK delta T. This one sometimes you may need to use it. This one is minus integration P respect to what? Okay. Again, if you have questions, I'm always available on WhatsApp. Chat with me if you need to. And I'll see you when the new year starts. Bye.